Okay. So we are happy to have Zhi-Hao Zhang from Shenzhen. He's going to tell us about a classification SPT, SET orders with on-site symmetries.
Okay, so let's start. This talk is based on our recent work, joined with Kong Liang, Lan Tian, Wen Xiaogang, and Zheng Hao. In this talk, I will explain a unified framework for the classification of symmetry enriched topological orders and symmetry protected trivial orders in all dimensions. Roughly speaking, SET order is a topological order with symmetries. So before we study SET orders, let me briefly review the notion of topological order. Microscopically, a topological order is a certain gapped quantum system at zero temperature. They are gapped quantum liquids. And macroscopically, a topological order can be described by the topological excitations up to invertible topological orders. Invertible topological orders have no non-trivial topological excitations. And a topological excitation is an excitation which cannot be created or annihilated by local operators. For example, in 2D, a 2D topological order can be described by the point-like topological excitations. And these topological excitations form a structure called the unitary modular tensor category, the UMTC. The objects of this category are anyons. They are labeled by X, Y, Z. And these anyons can be fused and braided. And they also satisfy a non-degeneracy condition. This condition says if the double braiding of X and Y is trivial for all anion Y, then X must be the trivial anion. This is the UMTC. So it is reasonable that SET order can be similarly described by the topological excitations up to invertible topological orders. However, this idea soon runs into problem. We will illustrate the problem in 2D SPT orders.
Sorry, is it my problem? I cannot hear.
I can't hear either.
I can hear.
Yeah, me too.
Somehow interrupted.
Oh gosh, I don't know what happened. I cannot hear him. Is it network problem?
Yeah, all of a sudden, it goes away.
Yeah.
Should someone tell him offline? I mean, off Zoom. I mean, he might not even know that he was kicked offline, or for whatever reason, disconnected.
Oh, if you have his WeChat, can you tell him that we cannot hear?
Oh, I think he's back. All right.
Is he back?
Seems like, I don't know.
No, maybe.
Still cannot see.
But I think we can't hear him yet.
Me neither.
Yeah.
Me neither.
Maybe he needs to log out and log back in. Sometimes.
Yeah.
Sometimes something just goes wrong.
Yeah, please tell him via WeChat or something, some other method. I don't have his contact. Tell him that please reboot Zoom again or something.
Well, I have informed him.
Oh, okay,
that
please.
he realized that, and he is trying to reconnect
Oh,
to
okay.
us.
So let's, I'm sorry about it. Let's wait one or 2 minutes.
Yeah, I think that's enough.
Yeah, I think he logged out and he's trying to get back in.
Yeah, he's trying.
Huh? Oh gosh. Still? Oh, he's now back. Can you?
But can we hear
I'm gonna
him?
doubt him again.
Oh, so again, I need to make it co-host, I guess. Sorry.
But can we hear him?
Can you speak? Zhi-Hao, can you speak?
I think he's just logging.
But we still can't hear him. Oh dear.
Oh gosh.
Oh, this is bad.
I made him co-host, so in principle he can share screen and he can speak, but we cannot hear him. Does he have some another devices? I'm sorry. I don't know how he connect. Or I'm very sorry. I hope the problem will be solved soon. Stay connected.
If he has a different device, or he has to restart completely, that's also a possibility. I don't know.
Is there any possible to use a cell phone
or some other iPad or something? Does he have?
Yeah,
that's so weird. It's
that's very weird.
you test the before the talk, right? We
That's
tested.
right. It worked very well. Nothing goes wrong.
Wait.
Oh yeah, he's
Oh
come
no, I
back.
can hear. Can you share
Can you
this?
share the file?
Okay, he's back.
Well,
Yeah, I can hear you.
can you hear me?
Yes.
Oh,
So can you share the screen? Now you
Okay,
should be
okay.
able to. Okay, good. Wonderful.
oh, okay. So
Yeah, please continue.
yeah. Oh, so where am I? So can we continue?
Yeah, please.
Oh, yes. Okay. So I should say it is reasonable that the SCT order can be similarly described by the topological excitations. But this idea soon runs into problems. We will illustrate the problem in 2D SPT orders. Here, SPT order is an SCT order satisfying the following condition. If we break in the symmetry, we will obtain a trivial topological order. So now we consider a 2D SPT order with an onsite symmetry G. Here G is a finite group. By the definition of an SPT order, there is no non-trivial topological excitations. So what are trivial topological excitations? Yeah, let me give an example. consider a Z2 symmetry of flipping the spins on all sides. Flip the spin up to spin down and spin down to spin up. And this symmetry can be realized by an operator tau. Tau is a product of sigma x operators on each side. Here sigma xi is a sigma x operator on the i's side. Suppose the ground state wave function is given by omega. Here omega is spin up plus spin down on each side. Then we consider an excitation psi. Psi is spin up plus spin down on all sides except on this side. It is spin up minus spin down. This excitation psi can be created by a sigma z operator on omega. Yeah, it is spin up minus spin down. And this Z2 symmetry acts on the omega as +1 and tau acts on psi as -1 because on this side it is spin up minus spin down. So we say the ground state omega carries the Z2 charge +1 and the psi carries the Z2 charge -1. So we can distinguish the local excitation psi from the ground state omega by their symmetry charges. Similarly, for a 2D SPT order with symmetry G, there is no non-trivial topological excitations. There are only local excitations, but the local excitations can carry symmetry charges. Symmetry charges means the representations. So they form a category of representations of the group G. This category is denoted by rep G. For bosonic symmetries, the topological excitations form a symmetric fusion category, and we still denote it by rep G. Here, symmetric means the double gradients are all trivial. And for fermionic symmetries, the fermion parity Z is contained in this group G, and the fermion parity counts the number of fermions. And we know exchanging two fermions gives a phase factor -1. So this provides a new symmetric braiding structure on the rep G. To distinguish two braiding structures, we denote the category rep G equipped with this new braiding structure by rep G, rep GZ. Here Z is fermion parity. So for fermionic symmetries, the topological excitations also form a symmetric fusion category, the rep GZ. If a SPT order is indeed described by the topological excitations, then we should expect that there is only one SPT order described by the symmetry charges. So they form symmetric fusion category rep G if the symmetry is bosonic. And for the fermionic symmetries, they form rep GZ. But on the other hand, it was known that there are many 2D SPT orders with symmetry G. And when G is bosonic, they are classified by the third group cohomology. And for the fermion parity symmetry, they are classified by Kitaev 16-fold way. So this is a contradiction. This contradiction tells us that the description of a SPT or SET order by topological excitations is incomplete. There must be some missing data in this description. So the question is, can we find the missing data? What are these missing data?
Sorry, can I ask one question?
Yes.
What do you mean? What do you mean by contradiction? I missed the point. What is the contradiction? Looks contradiction.
Yeah. The contradiction is if the SPT order is described by the topological excitations, the topological excitation is given by, say, rep-G. So there is only one rep-G, so there should be only one SPT order. But we know there are many SPT orders classified by the group homology.
Okay.
Yeah. So this contradiction says the description by topological excitations is incomplete.
Oh, okay. I see. I see. Okay. Thanks.
Okay. So one way to find the missing data is to gauge the symmetry. And we illustrate the idea by 2D SPT orders. Now consider a 2D SPT order with symmetry G. Levin and Gu introduced the process of gauging the symmetry by the following steps. First, the original symmetry transformations are global, but now we should consider local symmetries. For example, if the global symmetry is given by the Z2 symmetry of flipping the spins on all sides, then the local symmetries are flipping spins on only one side. However, the original Hamiltonian is not invariant under these local symmetry transformations. So we should introduce gauge fields coupling to the Hamiltonian. The local symmetry transformations will become gauge transformations, and the new Hamiltonian should be gauge invariant. And microscopically, this new Hamiltonian realizes a 2D topological order because the symmetry is broken. It is a topological order without symmetries. We call it the gauge theory of this SPT order. The topological excitations of this gauge theory are symmetry charges and gauge fluxes. They form a unitary modular tensor category, and this unitary modular tensor category describes the gauge theory macroscopically. And different SPT orders are distinguished by their gauge series. For example, we know there are two different Z2 SPT orders in 2D. And the gauge theory of the trivial one is the Topological or the Z2 gauge theory. And the gauge theory of the non-trivial one is a double Fermionic topological order.
What is the non-trivial here?
Well, there are two Z2 SPT orders in 2D classified by the third group cohomology of Z2. Yeah, so there is only one non-trivial Z2 SPT order.
I see.
Then, inspired by Levin Gu's idea, Lan Tian, Kong Liang, and Wen Xiaogang introduced the categorical formulation of the gauging process. Given a 2D SPT order, we know the topological excitations are only the symmetry charges, and they form a symmetric diffusion category E. And for bosonic symmetries, E is given by rep-G, and for fermionic symmetries, E is given by rep-GZ. Then we gauge the symmetry by introducing more topological excitations. These additional topological excitations play the role of gauge fluxes. And the symmetry charges and these additional topological excitations form UMTC, denoted by M. And this UMTC describes a 2D topological order, which is the gauge theory of the SPT order. And M should contain the symmetry charge E. This embedding is denoted by iota M. Then the pair M and this embedding iota M is called a modular extension of E because M is a modular tensor category. So this is the modular extension. But not all modular extensions describe a gauge theory. This is an example. Suppose M is a gauge theory. Then we can always stack it with another topological order n, and E can be embedded into M tensor n. This is still a modular extension, but clearly this double layer system does not describe gauge theory. To exclude these examples, we require that any additional particle Y should have non-trivial double braiding with at least one symmetry charge E. And in this example, an additional particle Y in the topological order n always have a trivial double braiding with a symmetry charge E, because they are in different layers. So such Y particles should be excluded. This requirement is equivalent to say, if a topological excitation Y has trivial double braidings with all symmetry charges, then Y cannot be different from a symmetry charge. In mathematics, the topological excitations in M which have trivial double braidings with all symmetry charges form a subcategory called the Milger centralizer. The Milger centralizer is denoted by Z2EM, the Milger centralizer of E in M. So this requirement is equivalent to say the Milger centralizer is equal to E. And a modular extension M satisfying this condition is called a minimal modular extension. Then the minimal modular extension provides a way to characterize the 2D SPT orders. So now we get a complete description of 2D SPT orders. A 2D SPT order with symmetry given by a symmetric diffusion category E is rep-G or rep-GZ. It is described by a minimal modular extension M and embedding from E to M. Here M is the UMTC of topological excitations of the gauge theory. So the 2D SPT orders with symmetry E are classified by the set of minimal modular extensions of E. This set is denoted by MEXE, the minimal modular extensions of E. And this is a mathematical theorem. It says for any symmetric diffusion category E, the set of minimal modular extensions is indeed a finite abelian group. Its unit is a trivial SPT order. And the group multiplication is given by the stacking of SPT orders. First, we can naively stack two SPT orders, and this double layer system have symmetry E tensor E. Then we should introduce the interactions between two layers and break the symmetry from E tensor E to E. And mathematically, this symmetry breaking process is realized by the Andian condensation. For bosonic symmetries, E is given by rep-G, and this group of modular extensions is given by the third group cohomology group. And for fermion parity symmetry, E is given by rep-Z2Z. And the group of minimal modular extensions is given by Z16. So this result recovers the Euler cohomological classification of bosonic SPT orders and Kitaev 16-fold way. And let me briefly mention that the idea of gauging the symmetry applies to 2D SET orders. For a 2D SET order, the topological excitations form a unitary braided diffusion category C. And as before, the symmetry charges form a symmetric diffusion category E. And in an SET order, C is usually larger than E because there are non-trivial topological excitations. And we gauge the symmetry, the gauge theory is described by UMTC M, and M, the additional particles in M has non-trivial double gradients with symmetry charges. So M is a minimum modular extension of C. Then the SET orders with topological excitations given by C are classified by the set of minimum modular extensions. And also, this idea can be generalized to higher dimensions, but we do not go through the details. So this is the first approach, the gauging the symmetry. And is there any question?
I mean, when you say that this idea can be generalized to higher dimension, what do you mean? I mean, what do you mean about? I mean, modular. How do you define modular tensor category in higher dimension?
Well, in higher dimensions, the topological excitations form a unitary modular N category.
Okay.
We should use higher categories to describe these topological excitations.
Mm-hmm.
But the minimum modular extensions still work.
Mm-hmm. So the UBFC means braided fusion category.
Yes, unitary braided fusion category.
Okay, thanks.
Okay. So the idea of gauging the symmetry works very well, but there are still some questions. The first question is, we cannot claim that we have found the missing data because an SPT or SET order is well defined before we gauge the symmetry. Yeah, so the gauging process is only a way to reveal the missing data instead of a description of the missing data. There should be a macroscopic description of SPT or SET orders without gauging the symmetry. The second question is, if a SET order cannot be gauged, then the idea of gauging the symmetry doesn't work. Okay, an SET order cannot be gauged is called anomalous, and we say it has a 't Hooft anomaly. Physically, it is known that an SET order can be gauged if and only if its bulk is a trivial SPT order. And in particular, the bulk of an SPT order is a trivial SPT order. This sheds light on another way to describe the SPT or SET orders.
I'm a little bit confused here. I guess, is there any way to understand this gauging? I guess here gauging you are talking about 2+1 dimension, right?
Well, but gauging, you can do gauging in any dimension, right?
No, here in your case, you just explained that from a SPT, you get some.
Well, yeah, but the gauging, yeah, we can do gauging in any dimension, but
yeah, that's my. I wonder. It seems this is different from the pure theory gauging. If I understand correctly, your H3 cohomology classification, which is essentially the classification of the 2D anomaly, right? Not 2+1D. If I have a 2D zero form symmetry, I classify 't Hooft anomaly, then you get H3, right? H3G U1.
Yes.
So
no.
my question is, do you have any understanding? Yes. Do you have?
I think he's talking about 4D to the anomaly. This is 2+1 SCT on the boundary of 3+1.
Yeah, that's not my question. My question is, do you have a boundary understanding of this gauging? What is the boundary correspondence if you think a boundary theory?
Boundary.
In your 2+1 case, in your 2+1 case, I understand that the later one, anomalous, maybe he referred to a higher or even higher, let's say 4D. But yeah, my question is simply, for this here, gauging, what is the understanding in terms of the boundary, 2D, say? 1 plus 1.
All
Yeah,
folding.
so you mean what is the boundary of a 2 plus 1D SET order? So this is your question?
I think the bulk here is a 3 plus 1D. SET is a 2 plus 1D, and the bulk is bulk SPT is a 3 plus 1D. So go up 1 dimension, not go down.
Yes. So here, and for example, a 2 plus 1D SET order can be gauged if and only if its 3 plus 1D bulk can be gauged. Its 3 plus 1D bulk is a trivial one. Yeah. The SET order is 2 plus 1D and the bulk is a 3 plus 1D.
I thought the question was like what gauging means on the boundary of 2 plus 1, right?
Yeah. That's my question.
I think that means orbifolding in the CFT if the boundary is a CFT. Something like that. But
Oh, is that okay? Okay, thank you.
Well, so let me reformulate this question. You say if I have a 2 plus 1D SET order and it has a boundary which is a 1 plus 1D SET order,
Yes.
and I gauge this 2 plus 1D SET order, what is the boundary? Yes?
Yeah, from your gauging, I thought your first gauging means that from SPT to some, right? Or maybe SCT. Yes, that's my question. Yes, essentially.
Well, I think the boundary is still the 1 plus 1D SPT order or SCT order. Well, yeah.
Yeah, so does that correspond to orbifolding as it suggests?
Well, maybe yes. Yeah, I'm not sure, but
I think in general, it's not. I mean, for bosonic case, they still have the gapped boundary in general. For bosonic cases, always have the gap boundary, but for fermionic, you will have a gapless boundary. In that case, you will have a like a orbifolding CFT or something.
I mean, what do you mean it's always gapped when it's bosonic?
They were talking about this is SET, right? I'm talking about SPT, or if the SPT in the bosonic case is just a gauge theory.
After gauge, maybe this is.
Yeah, after gauge, after gauge, it's known that there's still gapped boundary. It's still a non-chiral. Or for all H upper 3 cohomology. Yeah, but for fermion, yeah, they have a gapless stage.
I think let him go. I think we can discuss later.
Yeah, sure.
Yeah.
Sure.
Please go ahead.
well, hello?
Yes, I can hear you. Please speak. Please.
There is something wrong in my network.
Please proceed your talk.
Okay, so maybe I missed some discussion. Well, so yes. Yeah, before I explain the second idea of classification of SPT or SET orders, I'll tell you an important principle, the unique bulk principle. This principle says each ND topological order has a unique bulk, and this bulk is an n plus 1D topological order. So this principle seems very trivial, but it tells us many things. The first thing is, if the mathematical descriptions of bulk and the boundary topological order are known, then there should be a mathematical description of how to obtain the bulk from a boundary. This mathematical formulation is called the boundary bulk relation. And when the precise boundary bulk relation is known, the description and the classification of boundary series of a given bulk is also clear, because the possible boundaries are those topological orders whose bulk is the given one. Okay, so now our second idea of classification of SPT or SET orders is already clear. First, we need to know the precise mathematical formulation of the boundary bulk relation. Then we view 2D SPT orders as boundaries of the trivial 3D SPT order. The boundary bulk relation should provide the explicit description and the classification of 2D SPT orders. Yeah, this is our second idea.
Can I ask a question?
Yeah.
So what you mean is that a 2D SPT order can always has a bulk that is trivial 3D SPT order, and there is this principle that says that the bulk is unique, so you can view the bulk of the 2D SPT order as the trivial one, right?
Yes.
Okay.
Okay. So the first step is a boundary bulk relation. This is a mathematical formulation of the boundary bulk relation. So suppose we have an n+1D bulk topological order. It is described by a unitary modular n category, C, yeah, denoted by C. And the boundary topological order, the boundary ND topological order, is described by a unitary fusion n category A. Then the boundary bulk relation says C, this unitary modular n category C, is equal to the Drinfeld center of A. Here, the Drinfeld center is a mathematical object, and we don't need to know the precise definition. Yeah, so the boundary bulk relation says the bulk is the Drinfeld center. Yeah, that's the mathematical formulation. So we have known the mathematical formulation of the boundary bulk relation. The second step is to view 2D SPT orders as the boundaries of the trivial 3D SPT order. And then we use the boundary bulk relation. But in the boundary bulk relation, the boundary 2D topological order should be described by a unitary fusion 2 category. Yeah, we have only known that a 2D topological order can be described by a UMTC. This UMTC consists of particle-like topological excitations. So let me explain how to describe a 2D topological order by a unitary fusion 2 category. Given the 2D topological order M, its 1D domain walls and the 0D domain walls are also observable in the long wavelength limit. So they are also a description of this 2D topological order. They form a structure called unitary fusion 2 category. The objects are 1D domain walls, and the one morphisms are 0D domain walls. So in this figure, P, Q, S, and T are 1D domain walls, and A is a 0D domain wall between P and Q. B is a 0D domain wall between Q and S. C is an end of this 1D domain wall T. So it can be viewed as a 0D domain wall between T and the trivial 1D domain wall. This X is a particle-like topological excitation. So it can be viewed as a boundary of two, not boundary, a 0D domain wall between two 1D domain walls, two trivial 1D domain walls. Okay, and 0D domain walls can also be vertically fused. For example, A and B can vertically fuse along Q, and the result is a 0D domain wall between P and S. Also, the 1D domain walls can be horizontally fused. For example, So for example, we can horizontally fuse T and this trivial 1D domain wall. Then the associated 0D domain wall C and X are also fused. But these 1D domain walls cannot be braided because they are live in 2D space. So they cannot be braided. They only form a unitary fusion 2 category. It is known that 1D domain walls in M can be obtained by anion condensation. So they are condensation descendants. So we have two equivalent ways to describe a 2D topological order. The first way is to describe a 2D topological order by its particle-like topological excitations, which form a UMTC M. The second way is to describe a 2D topological order by the 1D domain walls and the 0D domain walls. And they form a unitary fusion 2 category M, sigma M. So this unitary fusion 2 category sigma M is called the condensation compilation of M. And similarly, in an n+1D topological order, the codimension 2 and higher topological excitations can be fused and braided. So they form a structure called unitary modular N category, denoted by C. The codimension 1 and higher topological excitations can be fused, but they cannot be braided. So they form a structure called unitary fusion n+1 category, denoted by sigma C. And sigma C is called the condensation compilation of C. And we can use C or sigma C to describe an n+1D topological order. And these two descriptions are equivalent. Okay, so now we come back to use the boundary bulk relation to classify 2D SPT orders. Recall our idea is the bulk of a 2D SPT order is a trivial 3D SPT order. Okay, so consider a 2D SPT order with symmetry E. We know the topological excitations are symmetry charges. There is no non-trivial topological excitations, and they form the symmetric fusion category E. E is rep G or rep GZ. To use the boundary bulk relation, we need to do condensation compilation, and the symmetry charges and their condensation descendants form a fusion 2 category, sigma E. And also, since E is symmetric, and this 2 category, sigma E, is also symmetric. Then, by the boundary bulk relation, the bulk 3D topological order of this 2D SPT order is described by the dreamfield center of sigma E. So what is this bulk topological order? It is the gauged series of the trivial 3D SPT order. In mathematics, there is a canonical embedding from sigma E to this dreamfield center, denoted by this iota 0. And this embedding is a trivial minimum modular extension of sigma E, which describes the trivial 3D SPT order. By our first approach, the minimum modular extension approach. Then the boundary bulk relation identifies the bulk 3D topological order with this gauged series of the trivial 3D SPT order. Yeah. And mathematically, this identification is a braided equivalence phi from the dreamfield center to itself. The left dreamfield center is the bulk 3D topological order. Yeah, it is given by the boundary bulk relation. The bulk is given by dreamfield center. And the right dreamfield center is a gauged series of the trivial 3D SPT order. It is a trivial minimum modular extension. And this identification should preserve symmetry charges because it is an identification between 2 SPT orders. So what are symmetry charges? Symmetry charges and the condensation descendants are given by sigma E. And sigma E embeds into the dream field center by this canonical embedding. So this diagram should be commutative. This phi is the identification, and sigma E are symmetry charges embeds into the dream field center by iota 0. And the phi preserves the symmetry charge means this diagram is commutative. This braided equivalence phi is the missing data. Yeah. So now we find this missing data. And all such braided equivalences phi between the dream field centers and another dream field centers form a group. These braided equivalence phi also preserve the canonical embeddings, and all such braided equivalences form a group. We denote this group by this notation, the braided outer equivalences of the dream field center, which preserves the iota 0. And consequently, 2D SPT orders with symmetry given by E are classified by this group. So now we have two classifications of 2D SPT orders with symmetry E. The first approach is for gauging the symmetry, and the classification is given by the group of minimal modular extensions. The minimal modular extensions describe the gauge theory. And the second approach is based on the boundary bulk relation. The classification is given by the group of braided auto equivalences of the dream field center, which preserve this embedding iota 0. So the natural question is, are these two approaches equivalent? Mathematically, this amounts to show that these two groups are isomorphic as groups. And this is a surprising mathematical conjecture, which deserves a mathematical proof. But now we don't have a proof yet. So we further clarify this relation between these two approaches. Physically, a braided equivalence phi from the dream field center to the self is achieved by tunneling through a 2D invertible domain wall. So what does this mean? It means if there is a invertible domain wall Wi-Fi between two dream field centers, the dream field center is a 3D topological order, then we can move a topological excitation in the left bulk to the right bulk through this invertible domain wall. And the domain wall is invertible means the moving a topological excitation from left to right is a braided equivalence of the dream field center. And this braided equivalence is 1-to-1 corresponds to the 1D domain walls, the invertible 1D domain walls. So we denote the 2D invertible domain walls. We denote this 2D invertible domain wall corresponding to phi by Y-phi. And what is this Y-phi? This invertible domain wall Y-phi is a domain wall between the 3D trivial SPT order and another trivial 3D SPT order. So Y-phi must be a 2D SPT order. This 2D SPT order is the 2D SPT order corresponds to phi. And also the gauging process can be recovered by closing this fan. And this folding process is a dimensional reduction. And mathematically, this dimensional reduction can be realized by this relative tensor product. And we claim it is equivalent to the condensation completion of the gauge theory M. And M is corresponds to phi, so we denote it by M phi. This provides a map from this autoequivalence group to the group of minimal modular extensions. And the equivalence of these two approaches is this map should be a group isomorphism. It will be important to find a rigorous proof of this conjecture. And as far as I know, some mathematicians have already started working on this conjecture. Okay. And the idea of the boundary bulk relation leads us to a unified classification theory of SPT or SET orders in all dimensions with higher symmetries and even the Houghton anomalies. Yeah, this is a unified theory. This is our main result. Says for an ND SET order with a higher symmetry given by a symmetric fusion N category R, and it is described by the following data. The first data is unitary fusion N category over R, A. This A describes the topological excitations, including condensation descendants. And M is a minimum modular extension of R, which describes the bulk N+1D SPT order. So it describes the Houghton anomaly of this SET order. And by the boundary bulk relation, there should be a braided equivalence phi from M to the dream field center A. And this braided equivalence preserves the symmetry charges. So this diagram should be commutative. And moreover, by allowing M to be non-minimal, we obtain a description of an SET order with gravitational anomalies. And this surprisingly unified framework provides a conceptual understanding of many known SPT or SET order classification results in lower dimensions. And as an example, we consider the 1D cases. By our general theorem, a 1D SET order is characterized by the following data. First, the symmetry is described by a symmetric fusion 1 category R, and the topological excitations form a unitary fusion 1 category over R, denoted by A. Then we need a minimum modular extension M, which describes the bulk 2D SPT order, which is the Houghton anomaly of this 1D SET order. And finally, we need a braided equivalence phi from M to the dream field center of A. Then the following diagram is commutative. Finally, we can simply check in the quantum dimensions, and we can prove the category A of topological excitations is equivalent to the category R of symmetry charges. So there is no non-trivial topological excitations. And this means SET order without gravitational anomaly is indeed a 1D SPT order. And then the minimum modular extension M is equivalent to the dream field center of R. So it is a trivial minimum modular extension. There is no Houghton anomaly. In other words, a non-trivial 2D SPT order has no gapped symmetry preserving boundary. Hence, the boundary of a non-trivial 2D SPT order must be gapless or symmetry breaking. These two physical results were well known and proved previously by other physical methods. Now they follow immediately from our general theory. So we only need to consider 1D SPT orders by taking the category A of topological excitations to be R, the symmetry charges. And the bulk 2D SPT order is trivial, the dream field center of R. Then a 1D SPT order with symmetry R is uniquely determined by a braided equivalence phi from the dream field center of R to itself such that the following diagram is commutative. And all such braided equivalences form a group of denoted by this notation. This group classifies 1D SPT orders. Then the group of braided automorphisms of the dream field center, which preserve this braided embedding iota 0, is isomorphic to the so-called Picard group. And for bosonic symmetries, R is given by rep-G. The Picard group is given by the second group cohomology. This result recovers the cohomological classification of bosonic SPT orders. And for fermionic symmetries, R is given by rep-GZ. The Picard group of rep-GZ is given by the following results. And this result also agrees with the physical classification result. Okay, so this is the 1D cases. And finally,
excuse me, can I ask a question?
Yeah.
So are you saying that the classification of fermionic symmetry, when it's GB times Z, it's just the bosonic times another Z2?
Yes, this Z2 is given by the Majorana chain.
Yeah. Oh, here's H up to G. Sorry, you not GB. Okay, all right. Yeah, that's fine. Thank you.
Yeah. Okay, so finally, I'll give a summary and some final comments. The topological excitations do not characterize as SPT or SET order. There are some missing data. And we can either find an equivalent characterization of the missing data by gauging the symmetry or by the boundary bulk relation. Both approaches can be generalized to higher dimensions. And we obtain a unified framework for the classification theory of potentially anomalous SPT or SET orders in all dimensions. In 0D and 1D, our general results agree with the physical classification results. I have shown the 1D cases. The equivalence of two approaches in 2D leads to many surprising mathematical conjectures, and a couple of which were proved after the appearance of our paper. And these two approaches are not independent. When we use a boundary bulk relation, its bulk must be gauged. If we do not gauge the bulk SPT order, then we use the symmetric center. The missing data is still invisible because the bulk is still SPT. It only have symmetry charts and we cannot find the missing data. We need to go to the higher bulk. If we do not gauge the symmetry at all, we will get an infinite tower of SPT orders. ND SPT orders have bulk. Their bulk are SPT orders in N+1D, and they still have bulk in N+2D. And if we gauge the symmetry in some dimension, this infinite tower will be truncated. For example, our second approach is a truncation in the N+1D. So it's possible to use this infinite tower to classify SPT or SET orders without truncation. Okay, thank you.
Thank you very much. Is there any questions?
Can I ask a question?
Yeah.
Yeah, so I have a question about the relation between the two approaches you mentioned. So in the first approach, whether it's SPT or SET, you gauge the symmetry by introducing additional fluxes, right?
Yes.
In the second approach, I mean, the starting point is a fusion two-category description of, either of the topological order. But a gauge flux, I mean, modulo some details or a defect in the first approach is in some sense, for zero form symmetry is an invertible domain wall. And that's presumably part of the data, the 1D domain wall data in your second approach. So in a way, in the first approach, you are supplying that information by gauging, basically including these particular defects that correspond to the symmetries. Is this correct? Is this so
Yeah.
that so in some sense you have this data, just not in the most mathematically complete form in the first approach.
Well, sounds well, maybe it seems very subtle. This is a subtle question, and
yeah, I just want to understand.
These fluxes are additional particles, and
right.
If we do not gauge the symmetry, they do not exist, right? And
right.
So
sure, that's true. Yes, but I think that's more like an issue of language, whether you do it or not. But
maybe I'll explain what are these fluxes in our second approach.
Right.
Okay. So for example, well, maybe this figure is not very well. Maybe suppose we have 2D SPT order. This boundary is a whole 2D SPT order, and there is a 2D SPT order on the upper boundary. Then the fluxes are okay. The bulk 3+1D topological order have fluxes, and these fluxes walk through this boundary is fluxes on their boundaries.
Yeah.
Well, for example, the 3+1D toric code, there are M strings. The M strings on the boundaries are M fluxes. The boundaries of the 3+1D toric code is 2D SPT order. The M string are not intrinsic topological excitations of the 2D boundary. Only the end of this M string.
Right.
Yeah, the end of the M string are also not intrinsic topological orders. They are fluxes. They are extrinsic.
But maybe again rephrase it. So flux, of course, is a particle, but I can, I mean, I should really, maybe I want to view it as a boundary between a trivial domain wall and some kind of non-trivial domain walls. So in your two-category picture, right, you have the particles as a boundary between domain walls, 0D excitations as boundary of domain walls of 1D domain walls. So maybe maybe my question is really about these fluxes being the boundary of some other domain walls, and these domain walls are symmetry domain walls of the SET or SPT.
Yes.
Okay, I think that answers my question. Thank you.
Okay.
Any other questions? Okay, if not, let's thank the speaker again for whatever method. So I will stop the recording now.